This is Radhika. I am going to discuss uh, about switchgear and protection video lesson. In this, we are going to discuss about the protection of transmission lines and feeders. In this, today we are going to discuss about the protection of transmission lines using distance and impedance relays. In last class, we discussed about the different faults likely occurred in transmission lines. Today, we are going to discuss about the protection of transmission lines using definite distance relays and the protection of transmission lines using relays. In distance protection of transmission lines, the distance relays is considered for the protection of transmission lines where time lag can't be permitted. Selectively cannot be obtained by over current relaying. So in this, the protection of transmission lines using distance or impedance relays. Distance protection is widely used protective scheme for the protection of high and extra high voltage EHV transmission and sub-transmission lines. The distance relay measures the ratio V by I at relay location, which gives the measures of distance between the relay and fault location. The impedance or resistance or reactance or admittance of a fault loop is proportional to the distance between the relay location and the fault point. An impedance relay measures the impedance of the line at the relay location. The relay depends for action upon the impedance between the point where it is located and the point of fault. If the V by I is less than Z, means the impedance of the line section being protected, the relay will trip instantaneously. If V by I is greater than impedance, it indicates that the fault is beyond the protected line and the relay will not trip. There are two types of distance relays. The distance relay is considered for the protection of transmission lines where time lag cannot be permitted, selectively cannot be obtained by overcurrent relaying. In distance protection is a widely used protective scheme for the protection of high and extra high voltage lines. The protection schemes measure the line impedance or a component of the line impedance at the relaying point as an indication of the distance of the line from the relaying point up to the fault point. Impedance relays or reactive relays or more relays are used for this purpose. The distance protection scheme is best explained by the by the illustrative zone radial system. Three steps of distance relays are required at each of the three locations A, B and C. We will see in diagram. Let us consider the relay at A for fault taking place within 80% of the zone, that is point 8 of AB. The first stage operates. The stage 2 operates with a time lag when the fault takes place between the end of the first stage and well into the feeder between B and C, generally 0.5 BC. In stage 3, in which the further time delay is provided for tripping acts as a backup to the relay at B and also to the final first two stages at A. This is the stages. These are the stages in this diagram. So, three zone distance protection scheme. In this in-feed A, B, C, operating time at stage 1, stage 2, stage 3. In stage 1, the first stage about 80% of AB, and in second stage it will be 80% of BC. Protection of transmission lines using impedance relay. For feeders fed from both ends, two distance relays will be necessary. One at each end, however, these will have directional features. Each relay will have three stages. The operation of the relay unit will depend upon the direction of fault current and the distance of the fault from the relay location. So, in these characteristics of three stage impedance relays, that will be XY axis, XR axis, and it is the stage 1, 2 and 3. The impedance will be Z1, Z2, Z3 will be increased. In this three zone impedance protection scheme having directional features, the contact circuit arrangement of the scheme is shown in this figure. When the direction of the current is proper, the contact of the directional unit are closed and the trip coil is energized through the first stage impedance relay contact. If the fault is in the first zone, if the fault is in the second zone, the timer contacts T2 close after a certain time delay. The timer coil being in this diagram, it is the impedance characteristics of three zone protection with directional unit. In this, it has the positive torque and negative torque, and it also has the directional relay. In this have three zones: zone 1, zone 2 and zone 3. It takes time T1, T2 and T3. The the impedance of the impedance will be increased in three zones. So in this is the contact circuit of three zone impedance protection. Activated by the closure of the third stage impedance unit. If the fault is in the third zone, then the timer contacts T3 close after further time delay. Thereby, the trip coil is energized. If the direction of the fault current is not proper, the directional unit contacts remain open and there is no way that the trip coil gets energized. The distance protection of transmission lines. The distance relay measures the ratio of V by I at relay location, which gives the measure of distance between the relay and fault location. The impedance means resistance or reactance or admittance of the fault loop is proportional to the distance between the relay location and the fault point. For a given setting, the distance relay picks up when impedance measures by it is less than the set value. Hence, it protects a certain length of line is called distance relay. Under normal conditions, these relays are used for face-to-face faults. This is the distance relay. in this in this distance protection of transmission line. So this is the time distance relay. So here in this, a simple power system with a time distance relays at power stations, substations ABC. The characteristics curves of the relays installed at the beginning of each section. Let there be a fault in between substation B and C. The time distance relay at substations B will trip in zero point 0.5 seconds, while the relay at substation A and at power station will operate in 1.05 and 1.53 seconds respectively. In in order that the fault may be cleared by the nearest circuit breaker, first the circuit breaker operation time should also be included. If the current breaker opening time is assumed to be 0.25 second after it trips contact energize, the breaker operation time is modified to the represented by dotted lines for substations A and B. Further, it will be obvious that the distance relays at substation A and at power station will act as backup relays for fault at point F. That is, if the relay at station B fails to operate, the relay of substation A will trip the circuit after 1.3 seconds, including time of circuit breaker, and even relay at substation A fails to operate, then the relay at power station will trip the circuit in 1.53 seconds. The definition distance relay, these are the in power stations it will be connected substation A, substation B and substation C, mean B, C, D. Here impedances ZA, ZB, ZC and ZD. The fault will be occur at substation C and substation D. ZA, ZB, ZC are the loop impedances of sections AB, BC and CD respectively. F is the fault and transmission line between CD. B, C, D substations, A generating station, Z impedance between fault and substation C. So this is the time distance relay. It has a power station, substation A, B and substation C. It has the fault. So in this, the above figure represents a simple transmission line consisting of substations B, C and D, etc. If a fault occurs at a point F between substation C and D, the loop impedance between fault F and generating station A and substations B and C are ZA plus ZB plus Z and ZB plus Z and Z respectively. The definite impedance relays at generating station A and substation B and C, etc. are said to operate with impedances less than ZA, ZB and ZA respectively. So, definition of the distance relay. In this, under this faulty condition, the relay at C will operate at open the circuit breaker. If the fault occurs between substations B and C, the relay at B will operate to open the circuit breaker. This is the time distance delay diagram. in this diagram. For the fault, the circuit breaker installed at A will open in 0.5 plus 0.2, that is 0.7 seconds. If the time impedance relay at A fails to operate, the relay at power station will close its contacts in 1.1 second and its CB will open in 1.1 plus zero point 0.2, that is 1.3 seconds. It is important that the circuit breaker at A should open before the relay at power station closes its contacts. Here the margin is 0.4 second. Now we will watch the one YouTube video regarding time distance relays.
Hi all, today we are going to see distance protection of transmission lines. So till now we have seen the overcurrent relays. The disadvantage with the overcurrent relays is the amount of the fault current depends on the type of the fault and also depends on the type of the neutral grounding. Like for example, for the solidly grounded system, we have seen in our last class that for 3-phase fault the current will be maximum. That's why it will cover up to maximum distance, because this IPU is the current that is set by the overcurrent relay. So at this point the current will be this minimum value. Why the current goes on decreasing? Because at the sending end the impedance will be only equal to the EMF generated divided by the source impedance. As you go on, the impedance of your transmission and will go on adding. That's why the amount of the fault current will goes on decreasing, and the point where it intersects with the current that is set, it will cover up to that much distance. Whereas if you go for other type of faults, that is line to ground faults or line to ground faults, it will cover the less distance. That is a disadvantage of the overcurrent relays. So we can conclude that the IF depends on the type of the fault. I am just briefly discussing about these things, which after that we will proceed for the protection using distance protection. So after this, let us take the effect of the source impedance. So if the source impedance is changing, because IF is equal to E divided by ZS1 when the fault happens near to the source. So as the value of the source impedance is increasing, automatically the value of the current will goes on decreasing. So the source impedance is also going to have the effect on the amount of the fault current. That is a second disadvantage of this overcurrent relays. So that's why practically we don't prefer to go for the overcurrent relays. We just use the overcurrent relays as the backup protection only, and the main protection will be done by the distance protection. That means using either impedance relay, reactance relay or the Moore relay. We are going to discuss about them one by one. So what is the basic working principle for this distance protection is, if you are taking E, ZS is my source impedance, here my relays will be there. It will measure the voltage using potential transformer and current using the current transformer. So at this point the ratio of this voltage and current is taken, which will measure the value of the impedance from this relay location up to the fault. So we will keep the value Z set. So how much value of the impedance it should operate? We know as the fault is happening farther away, so automatically the impedance goes on increasing. So it will protect up to this location of this fault. So if you take this transmission line, the voltage measured by the relay location is VR and the current measured by your relay is IR. Let us assume your transmission line I am representing by RL and XL. So here some fault happened. So now you can see the ratio of VR divided by IR, it will set in such a way, if it is less than the Z set, then it will trip, otherwise it will not trip. Or otherwise the impedance measured by your relay is less than the set value of the impedance, then your relay will operate, otherwise it will not operate. So how to get this one? To get these characteristics, what we do, we take one overcurrent relay and one voltage relay. So the overcurrent relay will act as the actuating quantity and this voltage will act as a restraining quantity. So using that we can get the impedance relay. So this we have already discussed in module number 3. So here I am directly skipping the things. I am only discussing briefly, and if you want details you can refer to our module number 3. That means lecture starting with series number 3. So there all these impedance relays are discussed in detail. So now the torque equation, we know that the universal torque equation can be written as K1 I square plus K2 V square plus K3 into V into I into cos theta minus tau plus K4. This K4 accounts for the spring or gravity. So this, if you are taking 1 as the voltage, because the torque is proportional to two fluxes, interaction of the two fluxes and sine of the angle between them. So that means sine of the angle between these two fluxes. So let us assume one flux is produced by voltage, another one by current. So in that case your equation will come in this way. And if both are produced by the voltage, it will become K2 V square. And if both are produced by the current, it will become equal to K1 I square. We will set it in such a way that this theta will be equal to 90 degrees. So we can directly write the square. So out of this, if you want to calculate get the impedance relay, you have to take the value of K3 is equal to 0 and the value of K2 and K4 as negative. That means we can tell that impedance relay is a overcurrent relay with voltage restraint. The voltage coil is acting as a restraining coil. Then we will get the impedance relay. Then if you want to go for the reactance relay is the overcurrent relay with directional restraint. Then we will get the reactance relay. And if you want to get the Moore relay is obtained by a directional relay with voltage restraint. Then it is called as the Moore relay. So after that we have summarized there that different relay characteristics. Let us assume this is my fault characteristics. So this line represents my fault characteristics. I want to protect up to this distance. Let us assume I want to protect up to this distance. So this can be either protected by impedance relay or reactance relay or the Moore relay. So this one is the characteristics. This outer circle is the characteristics for the impedance relay. So impedance relay, we take some radius of the circle. Generally the radius of the circle, to take it, so we will plot this point, this O to A. This indicates the radius of the circle. Generally the radius of the circle is taken, this angle tau or the maximum torque angle is taken in such a way that the maximum torque angle will be less than your value of the impedance, the impedance angle. The reason is, under fault conditions, what happens, because of the resistance of the fault, because of the fault resistance, so lesser than the value of theta, in order to account for compensation due to the resistance drop. That means if you want to protect the Z, let us assume this is my characteristic of the Z. Generally the radius at this inclined angle tau is taken as equal to Z set instead of taking here. Getting this one? Using that we can avoid the problem of underreach problem or the effect of arc. That means arc of the fault. So now coming to the reactance relay. So reactance relay will be protected at this point. So similar is the case if you want to go for the Moore relay, the Moore relay will be like this. So out of these relays, the impedance relay and the reactance relay are non-directional relays. So in order to provide the directional feature to that, one extra directional element will be added. So this is my directional element characteristics, and this tau whatever I told, it is corresponding to this directional element. Getting this one? And the Moore relay, the advantage is it covers very less area in the RX diagram. So it is less affected by the power swings, but the disadvantage is it is more affected by the arc resistance. That's why Moore relay is generally used for long transmission lines where the effect of power swing is more. And the second one, in the case of long transmission line, because impedance of line is more, so that impedance of line is so much dominating compared to the arc resistance. That's why that effect will be negligible. That's why we go for the Moore relay. And coming for the medium transmission line, we go for the impedance relay, because it is affected by the power swings but less affected when compared to the reactance relay. And only disadvantage of impedance relay is the effect of the arc resistance. So one thing is, by adjusting the value of tau, we can compensate it to some extent, and still the effect of arc resistance will be there. That's why this is generally used for medium transmission lines where the impedance is moderate, and by adjusting the angle tau, we can compensate for value of the arc resistance. And coming for the low lines, that means short transmission lines, then we go for the reactance relay. The reactance relay, the advantage of the reactance relay is it is independent of the arc resistance. It is not affected by the arc resistance, because in short transmission line, the impedance of your line is comparable to that of the arc resistance. That's why we go for the reactance relay. So I hope this is clear up to now. So let us proceed further. So the number of distance relays are used in association with timing relays, so that the power system is divided into the number of zones practically. Let us take, for example, I am taking a power system having the bus bars, one bus bar here, second and third bus bar. This is my entire transmission line. Please try to understand. So here one relay is kept in the beginning of the line as well as end of the line. So in the beginning of the line, every line is provided for protection in this direction, that means in the forward direction. That means the relay A, relay C and relay which is provided here, if some relay is provided here, this will provide against the forward direction, and relay B and D will operate only in this opposite direction. That means the directionality is provided in such a way. So now this relay A will operate for 80% of the first section, and then the remaining part, that means the remaining 20% plus nearly 40% of the second section will be covered by the zone 2 of the relay A, and again this remaining 40% up to the remaining part is covered by zone number 3. So you will get doubt why only 80%, why not we protect up to 100%. The reason is, we have discussed again in module number 3, there is, because of the DC effect, so there will be overreach of the relay. So whenever overreach happens, that creates a problem. In order to compensate for the effect of overreach, that overreach can happen with the change in the characteristic of your line plus the change in the characteristic of the CT and PT, or due to the DC component of the fault. So in order to compensate for that, that's why we protect for 80% only in the first zone, but we have to protect the entire remaining part also. That's why this is covered with a time delay, this remaining 20%, and some part of the second zone is also covered up to 40%, and then the remaining is covered by zone number 3. So here this y-axis indicates the time delay. Similarly, the relay at C, the C will be instantaneous up to 80% of this zone, that means in this section, then remaining 20% and remaining part will be covered in zone 2. So similarly in the opposite direction, B will operate in opposite direction, again B will be instantaneous up to 80%, and remaining 20% is covered by zone 2 of relay B. So similar is the case for relay D, it will cover 80%, then 20% plus 40% will be covered in zone 2, and remaining is covered in zone number 3. In this way we will protect it. So this zone number 1, the tripping is instantaneous and covers 80% of the protected zone, and zone 2 covers 20%, that means remaining 20% and 25 to 40% of the next section, and it will operate after some time delay, and zone 3 will cover the complete section with some more time delay. So let us see each one of the impedance relay for providing this zone protection, time zone protection. So what will be there? So this is my fault characteristics. So let us assume up to first section that 80% of the first section impedance will be, it will come up to this point, let us assume. So up to here we will set the impedance Z1. That means your first section, 80% of the first section impedance will be equal to Z1. This is my fault characteristics up to here Z1. Then from that 80% to 40% of the second section, including that one, is called as Z2. So that will be covered by the second impedance relay, which is located at same location A. So similarly, that remaining section will be covered by the third impedance relay. That means this third relay Z3 will cover the entire region from the beginning up to here with more time delay, and Z2 will cover up to here with some time delay, and Z1 will be instantaneous. That means if Z1 is not operated, after some time Z2 will operate, and after some time if Z2 is not operated, then Z3 will operate. That means this Z1, Z2, Z3, whatever are discussed here, that means zone 1, zone 2 and zone 3, this zone 1A, 1A will only cover up to 80%, and 2A will cover up to 140% of the from the beginning, but with some time delay. Due to some reason, if this relay is not operated, then this relay number 2 will operate. Then if relay number 2 is also not operated, then relay number 3 will operate with some delay. So this is coming to zone number A, and as well as along with this, this zone 2 and zone 3 will provide the backup protection for these areas that is in the adjacent sections. That means zone 2 covers about 40% of the section number 2, and zone 3 covers the remaining part of your transmission line. That means these are providing the backup protection for the remaining zones as well as the backup protection for the same zone also. So that is the advantage of this one. So let us see the impedance relays, how this will be connected. So here you can observe here this D indicates the directional, because impedance relay doesn't have the directional property. So this directional property is introduced by connecting a directional relay D. So this directional relay only if it operates then only your circuit will operate or your relay circuit will operate. Otherwise, your relay circuit will not operate. So let us assume some fault happened in some zone. Let us assume fault happened in the zone Z1. That means somewhere the fault has happened somewhere in this location. Somewhere the fault has happened in this location only. Let us take for example somewhere in this zone. So in this case, so both Z1, Z2, Z3 are active because all will start working. So now Z3 takes the maximum time, right? So whatever happens, whenever the Z3 is also activated, Z2 also activated, Z1 also activated. Now when the Z3 is activated, it will switch on the timer. So this timer will goes on increasing the time. This timer timings will be given to T2 and T3. Now Z1 is instantaneous relay because Z1 is also activated, Z2 also activated, Z3 also activated. So Z1 will operate immediately and it will trip the coil. So this is what is done, trip the coil of your circuit breaker. Let us assume that Z1 has not operated. Now what happens? After the time delay, after time T2, this Z2 will close its circuit and operate your trip coil. Let us assume that Z2 also not operated due to some problem. So now what happens? This T3, after time T3, the circuit is closed like this, then your trip coil will operate. So let us take for example, some fault is there in the between Z2 and Z3. Let us assume the fault has happened here. Some fault is there here. So in that zone what happens? Z1 is not activated, Z2 is not activated, only Z3 is activated. So now Z3 what it will do? The timer will switch on, and when the timer reaches the time T3, then this circuit will be closed like this and your relay will operate. So this is the auxiliary contact of your circuit breaker. Generally these auxiliary contacts are used for disconnecting the DC tripping circuit. DC tripping circuits, those are the power will not be wasted. Once the circuit breaker is opened, then this auxiliary switch will operate and open circuit your trip coil circuit. Open circuit your trip coil circuit in order to save the DC supply. So I am just summarizing here. So zone 3 element control the operation of timer and is the starting unit for this. So zone 1 elements operates without any intentional time delay. So Z2 and Z3 will operate with a time delay of T2 and T3. So if the fault happens in whatever zone, accordingly that corresponding relay will operate. So let us see how this can be done using the reactance relay. So for using the reactance relay, again reactance relay is a non-directional relay and it is so much affected by the power swings, and even it may operate under normal operating conditions also. Those disadvantages we have already seen in the reactance relays in module number 3. So how to overcome this? So what we will do, for zone 1 and zone 2 we go for the reactance relay, and zone 3 is provided by the Moore relay or admittance relay. This Moore relay provides the zone number 3. The advantage of Moore relay is only it will operate only within this region. So this zone number 3 whatever is there, that will be the starting unit because that will activate the timer and that will be connected here also. That means only if your fault is within this range of this zone number 3, then only your entire relay circuit will start operating. So let us assume that it is within this region, that means within this zone number 3. Then how this will operate? This S will activate, this else also will activate. So now it will activate the timer. So timer will goes on increasing. So now if it is within the zone number 1, then it is an instantaneous relay, so it will operate. Let us assume it is in zone number, between zone number 1 and zone number 2. Then this X2 will activate after time T2. Let us assume it is in between zone number 2 and zone number 3. Then it will, what will happen? So X1 and X2 will not operate. So after time T3, the circuit will close like this and your trip coil will activate. So in this way it will protect. So here you have to remember, wherever the reactance relay is there, the reactance relay is always used in conjunction with the Moore relay or a directional relay to avoid the mal-operation during normal operating conditions and the power swings. So directional property is compulsory. So but generally this reactance relay is used for short transmission lines. So because it is not affected by the arc resistance of the fault, that is the advantage of this one. So let us go to the next relay, that is a Moore relay. So the Moore relay, it is used for protection of the long transmission lines. So Moore relay setting will be like this. The first part, because this is my fault characteristics. So fault characteristics, this first part is provided by zone 1. That means up to the impedance of this much, zone 1 will be protected. Up to this much impedance, zone 2 will protect. and up to this much impedance zone 3 will protect, because it is by default having a directional element also, and it is very less affected by the power swings. That's why it is more suitable for long transmission lines. So here what will be there? Again, activating quantity will be the zone number 3 element. That means M3 will be the actuating quantity. Whenever the fault happens, M3 detects the fault, starts the timer unit. So now, if it is within the range of M1, instantaneous relay is activated, so it will trip your trip coil. Let us assume it is between the zone 1 and zone number 2. Then after time T2, M2 will close and close the circuit. Let us assume it is between zone 2 and zone 3. Then after time T3, the circuit will close. In this way, the relay will operate. So now, generally the time delay between two adjacent zones is provided. That time delay will be equal to the time required for the circuit breaker to operate, because whenever the circuit breaker contacts are open, there the arc will be produced between them. That arc should be extinguished completely. So that takes some time. So that much time delay is always provided between adjacent zones, so that the mal operation will not be there. That means the minimum possible section of the transmission line only is protected. So I hope the distance protection of the transmission lines is clear to you. If you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you. Thank you very much.
Now we watch the one YouTube video regarding protection of transmission lines using distance and impedance relays. In this lesson, we have discussed about the protection of transmission lines employs distance protection. Distance relays are designed to operate on the basis of impedance of the transmission lines. Definite time is maintained to close the relays between different substations and power stations. So here we have the few quiz questions and frequently asked questions. And thank you. In next class we will discuss another topic. Thank you.